Salam, peace be upon you. My name is Muhammad Laik Siddiqui, the father of Holophase. In part 23, we learned how a defect becomes countable. An integer charge is the winding you read from any oriented loop that encloses the obstruction inside the clean domain. Now we learn the next grammar rule, how charges combine when enclosures combine, and why a charge cannot change unless your boundary truly crosses an obstruction. You and I are standing over a wide table, and on the table there is a sheet of paper. It looks ordinary, but if you run your finger across it, you feel something. A few raised bumps, tiny ridges. They are not ink, they are not drawings. They are little places where the paper has been pinched, folded, and pressed. The smooth surface is interrupted. Now I give you a rubber band and I say, place the band on the paper, make a loop. You place it and you circle one bump. You can stretch the band wider, you can squeeze it tighter. You can make it oval or jagged or almost a circle. You can slide it around the bump. But as long as you keep the bump inside the loop, one fact remains unchanged. Your loop encloses that bump. Then I say, now circle two bumps at once. You do. You make a bigger loop that encloses both. And again, you can deform it all you want. As long as you keep both bumps inside, your loop encloses the pair. Now I ask you the question that part 24 answers. If each bump has an integer count attached to it, what is the integer count of the loop that encloses both? And second, if you keep enclosing the same bumps, can the integer count change just because you reshaped the loop? Those two questions are additivity and conservation. And in Holophase, they are not physics laws. They are not statements about forces or motion or what the universe does. They are grammar laws, syntax laws, closure laws. Because in episode 13b, we are freezing the language. We are not doing experiments. We are not doing dynamics. We are not doing what happens. We are installing what counts as a legal sentence. So let's hold the core listener picture in one breath. Charges compose like arithmetic because loops compose like language. Charges add for disjoint enclosures, and they are conserved under admissible deformation unless your boundary crosses a defect, meaning unless the topology of what is inside changes. Now we build it carefully in the simplest language possible, with every term made audible. We have one primitive, phi. Phi is a mapping from X to S1, spoken. Phi maps the event support X into the phase circle S1. X is not spacetime. It is only the minimal support that lets us talk about patches and overlaps. S1 is the circle, the cyclic order. To do calculus like speech, we locally lift phi. A lift is a local unwrapping of the circle into the real line. The lifted phase is called phi tilde. It is real valued. It exists only on lift valid patches. And it is not unique. You can add a full turn, 2 pi times an integer, and you still represent the same underlying phi. From phi tilde, we define our first change word, A. We say it out loud. A equals d phi tilde. A is the differential of the lifted phase. It is the local change report. It is the earliest public object of change in the language. Then we have finite jets, j to the n phi. A finite jet is the list of derivatives of phi tilde up to order n on a patch, with declared regularity type. If you did not license that smoothness depth, speaking at that depth is not a sentence. Then we have domains. In particular, we have the clean domain D. D is where derivative language is legal, where lifts and jets exist with the declared type. We do not pretend D is everything. We obtain D by excising neighborhoods around hazards, especially defects. Defects are obstructions. Part 22 installed that. A defect is not an added object. It is a place where the smooth story fails, where you cannot choose a smooth lift consistently, or you cannot extend jets with the declared regularity. Because of that, we remove a small neighborhood around defects from the legal domain. That excised neighborhood is part of meaning. No excision, no honest calculus. Now, loops. A loop is a closed path that stays inside D. It starts at a point in D, travels through D, and returns to its starting point without leaving D. A loop must also have orientation, a declared direction of traversal. Orientation matters because integers have sign, plus and minus. Part 18. Installed winding. When you traverse a closed loop in D, the cyclic nature of S1 forces an integer wrap count. Part 21. Installed homotopy invariance. In defect-free domains, if you deform a loop continuously while staying in D, its winding and holonomy do not change. Shape does not matter. Class does. Part 23, then installed defect charge. The integer winding you measure by an oriented enclosing loop around a defect neighborhood in D. In audio form, charge equals 1 over 2 pi times the closed loop accumulation of d phi tilde. But the deeper point is, charge is an integer token of obstruction, stable under admissible redescription. Now part 24 asks, once we have charges, how do they behave when we combine enclosures? And when do they change? The answer is simple, and it is forced by the grammar. Additivity comes from loop composition. Conservation comes from homotopy invariance plus domain honesty. Let's make loop composition feel like ordinary language first, because that is exactly the analogy the Holophase approach wants you to carry. If I say one sentence, and then I say a second sentence, I have made a longer statement. The meaning of the whole is the composition of meanings. Language composes. It has grammar for and then. Loops compose the same way. A loop can be traversed, and then another loop can be traversed. You can stitch them end to start, making a combined journey. That is loop concatenation, doing one loop after the other. Now, here is the key. The winding of the combined journey is the sum of the windings. Because you wrapped around the circle however many times the first loop wrapped, and then you wrapped however many times the second loop wrapped. Wrap counts add. So additivity is not a new axiom. It is the arithmetic shadow of the fact that you can do one loop and then another. But the language must also tell you when one big loop around two defects is equivalent to a composition of two loops, each around one defect. That equivalence is not always automatic. It depends on whether the domain allows you to deform one boundary into the other without crossing defects. This is why Part 24 is a syntax-level law. It is not about what defects physically do. It is about what boundary sentences are equivalent in the grammar. Now picture it again in a way that sticks. Imagine there are two thumbtacks on a board. A rubber band around both can sometimes be pulled into a shape like a figure eight. One lobe around the left tack, the other lobe around the right tack, with a narrow waist between. If you can do that deformation without letting the band pass over a tack, then a single enclosure around two obstructions is equivalent, in the loop grammar, to a composition of two enclosures. And then the winding of the whole is the sum of windings of the parts. That is additivity. Now, conservation. Conservation is even cleaner. It says, if you deform your enclosing loop in D without crossing defects, the integer cannot change. Why? Because charge is defined as a winding integer, and winding is invariant under admissible deformation in D. That is homotopy invariance. So conservation is not a separate postulate. It is simply what the language forces you to conclude if you are consistent. But we must be extremely strict about what deform means here, because we are not smuggling time. We are not describing evolution in time. We are describing movement in the space of allowable descriptions. If you redraw your loop slightly differently, but it encloses the same defects and stays inside D, the integer must remain the same. If it does not, then something has gone wrong in your typing. You crossed the defect neighborhood, left D, or your computation depended on an arbitrary branch cut. This is why conservation is a firewall. It forces you to debug your language before inventing new ontology. Now I will embed the 4 gates, not as a list on a blackboard, but as habits of speech that keep us honest. First, the well-formedness gate. You cannot talk about additivity unless you have well-formed child statements to add. Each child statement requires an oriented enclosing loop in D. It must specify what defect neighborhoods are enclosed. The loop must not cross excised regions, and the orientation must be declared, because a reversed loop flips the sign. So a well-formed additivity claim sounds like this in ordinary speech. I have one oriented loop enclosing defect 1, giving integer q 1. I have a second oriented loop enclosing defect 2, giving integer q 2. I have a third loop enclosing both, and the domain allows me to deform it into the composition of the first two without crossing. Therefore, the charge of the third equals q1 plus q2. Notice what is not allowed: hand waving. Charge is just add. In this language, you must show the grammar reason: loop composition plus admissible deformation. Second, the invariance gate. Once a charge is well formed, it is invariant under admissible changes of description. Shift phi by a constant phase, shift the lift by full turns, change charts, move branch cuts as bookkeeping, and deform loops within D without crossing defects. Therefore, the additivity relation must also be invariant. You should not get Q1 plus Q2 in one chart and Q1 plus Q2 plus 1 in another. If you do, you have not found new physics. You have found a failure of invariance, usually cut dependence or an illegal domain crossing. Third, the domain gate. This is the heart of conservation. Charge is only defined on loops that live in D. Deformation is only admissible if the entire deformation keeps the loop inside D, and if it does not change which defect neighborhoods are enclosed. So conservation is not magic. It is a conditional statement, and the condition is domain integrity. If the boundary crosses a defect neighborhood, meaning the enclosed set changes, then of course the charge assigned to what is inside can change, because what is inside has changed. That is not a violation. That is the precise event that permits change. This is why the listener picture says, charge changes only when inclusion class changes. Fourth, the non-encodability challenge. This is the discipline that prevents superstition. If someone claims charge drift without crossing, meaning they claim the integer changed even though the loop stayed in D and enclosed the same defects, the first response is not to invent a new primitive cause. The first response is to audit the sentence. Did the loop truly stay in D? Did it accidentally cross an excised neighborhood? Did the person forget a hidden defect? Did the computation secretly depend on a branch cut placement? Did they mix orientations? Did they confuse two loop classes that are not homotopic in D? In Holophase language, charge drift without crossing is a red flag that almost always means bookkeeping failure. Now, I want to make this feel inevitable, not like a rule we imposed. The easiest way is to show you a universal pattern. Conservation is what happens whenever you count something defined by inside and your boundary does not let the inside change. Everyday human reality. Imagine counting people in a room. If the doors are closed, the count is conserved. People can move around, that's a deformation. The count does not change. The count changes only when someone crosses the doorway, the boundary. That is exactly our situation. Defects are inside. The loop is the doorway. Charge is the integer count. As long as the set inside doesn't change, the integer can't change. History and behavior. Think of a city surrounded by walls in ancient times. Inside the walls, there are a certain number of households. People move within the city. The internal arrangement deforms. But the count of households changes only when households are created or destroyed, or when people cross the gates and settle or leave. In other words, boundary crossing events and inclusion changes. We are not claiming households are defects. We are using the grammar, stable counting under stable boundaries. Biology. Think of a membrane-bound compartment inside a cell. Molecules swirl and collide inside. The configuration deforms constantly. But the number of a certain molecule inside the compartment changes only when molecules are created or destroyed inside, or when they cross the membrane through channels. Again, change occurs through events that alter inclusion. The membrane is your loop. The inside set is your enclosed defects. The count is your charge. We are still not importing biochemistry as primitives. We are showing the same deep structure. Conservation is counting plus boundary integrity. Music. A measure in music is a boundary. Within the measure, notes can be rearranged and ornamented. But the number of beats in the measure does not change unless you change the time signature, unless you change the boundary convention. This is another form of domain and typing. Conservation depends on keeping the declared structure fixed. Weaving. If you count motifs inside the border of a rug, the count is stable under minor deformations of the fabric. It changes only if you change the border, or if you discover a hidden defect in the pattern, the change is what counts as insight. Across scales, the same discipline appears. If you define a count by enclosure, the count is conserved as long as your enclosure is not crossed. Now, in pure file language, we can state the same idea in the most rigorous, simplest way. Charge is an integer invariant of a loop class in D, determined by which defects the loop encloses. Under admissible deformation within D that preserves inclusion, the integer cannot change. That is conservation. Additivity is the extension. When a loop enclosing multiple defects can be decomposed by admissible deformation in D into a composition of loops each enclosing individual defects, the total charge equals the sum of individual charges. Now we must phrase the formal prediction and falsification in the episode 13b manner. Grammatical, not empirical. Prediction. Integer charge changes only when obstruction crossing events occur, which in syntax language means only when inclusion class changes. So if you keep the same enclosed defect set and stay in D, the integer cannot change. Falsifier. Show charge changes under a deformation that provably stays in D and provably crosses no defects. That would contradict the invariance grammar. If it happened, it would mean either you mistyped the domain, missed an obstruction, or your definition of charge was not truly cut independent. Now the triunity must remain alive throughout, so let me seal it here in the cleanest possible way. Remember, omega, kappa, nu are three inseparable readouts of A. Omega is temporal cadence, kappa is spatial texture, nu is kinematic transport. We do not treat them as independent primitives. There are three ways the same A can be read. A charge is a constraint on the global accumulation of A around a closed boundary. Therefore, conservation of charge is not a law about how omega changes in time. It is the statement that the integer packaging of the triaco accumulation around the boundary cannot change under admissible boundary deformation unless the boundary crosses an obstruction. So when you hear conservation, do not imagine a force preventing change. Imagine grammar preventing inconsistency. The integer cannot change smoothly because it is an integer. A continuous deformation cannot continuously change an integer. It can only stay the same until a discrete boundary crossing event changes what inside means. That is why this arithmetic is unbreakable. It is the arithmetic of closure. Now, we end with a memorable carry sentence and the bridge. Carry sentence. Charges add because boundaries compose, and charges are conserved because integers cannot change under admissible deformation unless inclusion changes. And now the bridge. Part 25 will take us into the next bookkeeping layer, when there are multiple defects. Sometimes it is not only which defects are inside, but how the loop links them that matters. Linking introduces structure that cannot be reduced to simple inclusion. It is still grammar, still topology, still PS0 clean, but it is a richer global sentence. Now, as promised, I will close with a concise summary of Part 24. Concise summary of Part 24. Building on Part 23, where a defect charge is defined as an integer winding read from an oriented enclosing loop in the clean domain D, Part 24 installs two syntax-level rules: additivity and conservation. Additivity states that charges combine like ordinary integers because loops combine like language. When a boundary enclosing multiple disjoint defect neighborhoods can be deformed within D into a composition of boundaries each enclosing individual defects, the total charge equals the sum of the individual charges. Conservation states that a charge cannot change under any admissible deformation of the enclosing loop that stays entirely in D and does not cross defect neighborhoods. The only permitted way for a charge to change is when the inclusion class changes, meaning the boundary crosses an obstruction so that a defect enters or leaves the enclosed set. This is not a law of motion, but a closure grammar. Since charge is an integer token of the global accumulation of A, where A is defined by A equals d phi tilde on lift valid patches, the integer cannot vary continuously under legal redescription. The well-formedness gate requires correctly typed loop concatenations or disjoint enclosures with declared orientation. The invariance gate requires both charge values and additivity relations remain unchanged under admissible chart and lift changes. The domain gate requires the entire deformation remain within D with explicit tracking of which defects are enclosed. And the non-encodability challenge says any claimed charge change without crossing is first diagnosed as bookkeeping failure, wrong domain, wrong loop class, hidden obstruction, or cut dependence. The formal prediction is that charge changes only at obstruction crossing inclusion changes. The falsifier is a demonstrated charge change under a deformation that stays in D and provably crosses no defects. Always peace be upon you.